Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 is a scenario where a titration was performed between a monoprotic weak acid and a strong base, and they found that the pH of the half neutralization point was 3.5. What is the pKa of the weak acid? Okay, so question 1. So first, let's define what happens at half equivalence point, or in their case, half neutralization point. At half equivalence point, this means that half of our acid is neutralized. Okay, so let's recall a neutralization reaction where we have a weak acid, and when it reacts with a strong base, this makes salt and water. So we don't know what the weak acid is, so that's just why I wrote out a general reaction. So at half equivalence point, if half of the acid is neutralized, then this means that our concentration of salt would be the same as the concentration of our acid. So since half of the acid is neutralized, then that means it made half the amount of salt that it would. And since everything is 1-to-1, because we know it's a monoprotic weak acid, then we can say that the concentration of the salt is the same as the concentration of the acid. So now that we know the concentrations at half equivalence point, we can plug them into the Henderson equation. So the Henderson equation relates pH and pKa, and it includes the log of the concentration of our salt over the concentration of our acid. So the salt can also be referred to as the conjugate base. So we don't need to have any actual values because we know that the salt concentration is equal to the concentration of the acid. So we can rewrite this equation, and when you divide the same concentration over the same value, you just get 1. So now let's plug in our pH to this equation. The pH was found to be 3.5. And when you take the logarithm of 1, then it is just 0. So therefore, our pKa is 3.5, which is the same as our pH at the half equivalence point. Okay, so now let's see what the junior tutor said. They said that the pH is a measure of how acidic or basic water is. It goes from 0 to 14, with 7 being neutral. pH values lesser than 7 is acidic, while pH values greater than 7 is basic. In this problem, we are asked to find the pKa of the weak acid. To do this, first write down the equation reaction. The problem stated that a titration was performed between a monoprotic weak acid and a strong base. When this titration happened, formation of a salt happened as a result. This acts as the buffer solution. Then the equation reaction is monoprotic weak acid plus a strong base makes salt and water. Step 2 is use the Henderson-Hasselbalch equation. It relates the pH of an aqueous solution of an acid to the acid dissociation constant of an acid. It is given by the equation. So they just defined all the terms. And from the reaction, the concentration of an acid is equal to the concentration of our monoprotic weak acid, and the concentration of the conjugate base is equal to the salt. Note that that half of the acid is neutralized, so the monoprotic weak acid's concentration is equal to the concentration of the salt, and we also know that pH is 3.5. So when they plugged everything into the Henderson-Hasselbalch equation, they also got a pKa equal to 3.5. So this solution is correct. Okay, so question number 2. At 25 degrees Celsius and 795 torr, carbon dioxide has a solubility of 0.0356 moles per liter in water. What is its solubility at 25 degrees Celsius and 1850 torr? So to answer this question, we are going to use Henry's law. So Henry's law is a pretty simple equation. It is S is equal to K times P. So in this case, S refers to solubility. K will be referred to as Henry's law constant. So this K value isn't an actual value, like it varies depending on the temperature and also depending on the type of substance we have. And P is just pressure. Okay, so step 1 of answering this question is to calculate for your Henry's law constant at 25 degrees Celsius. So given in the question, we know that the solubility was 0.0356 moles per liter. And we're trying to solve for K. And it has this solubility at 795 torr. So now we just have to solve for K. So 0.0356 moles per liter divided by 795 torr gives us a K value of 4.478 times 10 to the negative 5, and the units is moles per liter divided by torr. Okay, so we have our K value at 25 degrees Celsius for carbon dioxide. So now we can find our molar solubility at 1,850 torr. And again, we're going to use Henry's law. S is equal to K, which we found in the previous step was 4.478 times 10 to the negative 5 moles per liter over torr. And the pressure this time is 1,850 torr. So if we multiply these two, you end up with a molar solubility of 0.0828 moles per liter. Okay, so now let's see what the junior tutor said. The relationship between pressure and solubility of a gas at a specific temperature is shown in Henry's law. So they have C equals Kp, where C is the solubility of the gas in terms of the molar concentration, P is the external pressure, and K is Henry's constant, which is different for every substance at different temperatures. Determine Henry's constant based on the first given conditions. Okay, so they have C is equal to K times 795 torr, and they got a K value of around 4.5 times 10 to the negative 5. Yep. And now they computed for the solubility in the second condition given. Use the computed value of Henry's constant. So they just plugged in their K value and ended up with the same solubility, around 0.083 moles per liter. So this solution is correct. Okay, so question number 3. If you were studying an enzyme that catalyzed the reaction of ATP and fructose 1-phosphate to form fructose 1,6-bisphosphate and ADP, and discovered that a plot of the initial velocity of the formation of fructose 1,6-bisphosphate versus ATP concentration was not hyperbolic, but rather sigmoid, what would you expect? Okay, so let's try to graph out what this plot might look like. And we are plotting the velocity, initial velocity, which is V0, versus the formation of fructose 1,6-phosphate versus ATP concentration. I'm just going to put the concentration of our substrate. And for a common enzyme, this graph looks hyperbolic. So it kind of looks like this. And this is the graph of a common enzyme. But in our case, we have a sigmoid graph, or a sigmoid looking plot. And when you have a sigmoid plot, it kind of looks like this. And you can see it's kind of shaped like an S. So when we have a sigmoid curve, this tells us that our enzyme is allosteric. So let me write that down over here. When we have a sigmoid curve, also known as an S curve, this tells us that our enzyme is allosteric. And when we have an allosteric enzyme, this means that the binding of one substrate to the enzyme's binding site increases the affinity of other substrates or of other sites for their substrates. Okay, so for example, was the enzyme that catalyzed the reaction of ATP and fructose 1-phosphate to form fructose 1,6-bisphosphate and ADP. So when the binding of that one substrate to the enzyme's binding site actually increases the affinity of other sites for their substrates. And you can see how the concentration or the velocity increases rather quickly, and then it kind of plateaus off as the reaction continues. So let's see what the junior tutor said. They said that a sigmoid plot of the initial velocity of the formation of the product versus the concentration of the substrate signifies that the enzyme involved in the reaction is an allosteric enzyme. Allosteric enzymes are enzymes having at least 2 or more active sites. If the inhibition is competitive, the substrate may bind to the other sites while another substrate was occupying the desired active site. If it is non-competitive inhibition, on the other hand, there will be no effect in the plot of the initial velocity of the formation of product versus the concentration of the substrate. Therefore, in the case of the study involving the enzyme that catalyzed the reaction of ATP and fructose 1-phosphate to fructose 1,6-bisphosphate and ADP, the observed plot for the reaction was sigmoidal, probably because the enzyme used was an allosteric enzyme that have at least one active site competing for the substrate. Yep, so this solution is correct. I'll also add what I wrote as well. Okay, so on to question number 4. Your lab bench is 36 inches by 120 inches. How many square meters of acid-resistant film will you need to purchase to cover the bench? So we want our area in squared meters. And we're given the dimensions in inches. So the first step is to convert your inches to meters. And we would use the conversion factor where 1 meter is equal to 39.37 inches. Okay, so first let's look at our length. Our length is 120 inches. And then we just need to multiply by our conversion factor, having our desired units at the top, so 1 meter, and the units we're trying to get rid of at the bottom, so inches. So now if we multiply our dimension by this conversion factor, our value for inches will cancel out, and it's the same thing as saying 120 divided by 39.37. And this gives us our length in meters, which is 3.048. Okay, so now let's do the same thing for our width. Our width is 36 inches. And again, we're going to multiply by our conversion factor, 1 meter over 39.37 inches. And we get a value of 0.914 meters. So now the second step is to then calculate the area of the bench in meters squared. Okay, so it's just basic math. We know that area of this bench is equal to length times width. So we just plug in our values in meters that we found in the previous step. So 3.048 meters times 0.914 meters. And this gives us our area, which is 2.79 meters squared. Okay, so now let's see what the junior tutor said. Step 1 is to convert the dimensions into meters. So they used the same conversion factor and they kind of rounded it off, but they got the same answers, 3.05 meters, 0.914 meters. And when they multiplied the two, they also got 2.79 meters squared. So therefore, you need at least 2.79 square meters of acid-resistant film to cover the bench. So this solution is correct. Okay, so question number 5. How many protons, neutrons, and electrons are there in one atom of 209 Bi? So this is the symbol for bismuth. So I'll also just write it here. and Bi stands for bismuth. So the first thing we want to do is locate bismuth on the periodic table. Use this. Actually, kind of dark. And we can find it right here. And we're interested in its atomic number. So bismuth has an atomic number equal to 83. So the atomic number tells us how many protons bismuth has. So therefore, we have 83 protons. And the 209 is the atomic mass of our isotope. So I'll just write that here. 209 Bi has an atomic mass equal to 209. But if we recall the formula for atomic mass is equal to the number of our protons plus the number of neutrons. So now we can solve for our number of neutrons. So number of neutrons is equal to atomic mass minus your number of protons. So we know both of these values. We know the atomic mass is 209, and we also know our number of protons is 83. So therefore, the number of neutrons is 126. Okay, and lastly, we need to find our number of electrons. So if we have a neutral atom, we know that our number of protons must be equal to the number of electrons. So since we have 83 protons, that means that we also have 83 electrons. Okay, so these are our three values. We have 83 protons, and we know that from the atomic number. And we have 126 neutrons, and we got this value from subtracting the number of protons from atomic mass. And finally, we have the same number of electrons as we do protons, so we also have 83 electrons. So now let's see what the junior tutor said. Step 1 is to determine the number of protons and number of bismuth, I'm guessing atomic number of bismuth, using a periodic table. The atomic number is also the number of protons it contains, so we have 83 protons. Step 2 is to determine the number of electrons for a neutral atom. The number of electrons is equal to the number of protons. That's also 83. And then for step 3, to determine the number of neutrons given the mass number, which is 209, the number is the sum of the number of protons and the number of neutrons. So they got 126 neutrons. Okay, so this solution is correct. Okay, so now we're on to question number 6. So we have a graph or a diagram of free energy versus the fraction of A that reacted. Question A, what is the sign of delta G for this reaction? And B, what is the sign of delta G initially before A reacted? So let's try to draw this graph as well. So we have G, and down here we have the fraction of A reacted in thirds. And it looks like we have a minima in our graph right at 0.33. I'm just going to roughly sketch this out. Starts off like here, and then a minima, then it just kind of shoots up. Okay, so now for part A, what is the sign of delta G for this reaction? So we know that delta G of a reaction is equal to delta G of our products minus the delta G of our reactants. So if we look at our graph, you can see that the Gibbs free energy of our reaction increased as more A reacted. So this tells us that the delta G of our products is greater than the delta G of our reactants, and this tells us that the delta G of our overall reaction would then be positive. If the delta G of our reactants was greater than the products, then we would get a negative delta G. Okay, so that's part A. And then for part B, I'll write over here, what is the sign of delta G initially before A has reacted? So first, let's find our equilibrium point, which is the minima in our graph. So at equilibrium, delta G of our reaction is equal to 0. And this is also the minima of our graph. So it's shown here, so let me just label it. So after equilibrium, our free energy of the reaction increases. So you can see that it shoots straight up as delta G is positive. So this tells us that initially delta G of our reaction is negative. Okay, so let's see what the junior tutor said. Delta G for the reaction is calculated by the delta G of our products minus the delta G of our reactants. Since the diagram showed that the free energy increased as more and more fractions of A were reacted, it means that the delta G of the product is greater than that of the reactants. Therefore, the sign of delta G for this reaction is positive. Yep. And there is a point in the graph where G reached a minima, the lowest point in the graph, which means that the equilibrium is reached. Equilibrium is when the delta G of the reaction reaches 0. After that, the G increases, which means that delta G becomes more negative. Therefore, the sign of delta G initially should have been negative. Okay, so this solution is correct. Okay, so question number 7. What types of intermolecular forces are expected between this molecule? Indicate with a yes or a no. Dipole forces, induced dipole forces, hydrogen bonding. Okay, so let's try to draw out this molecule. We have CH3, CO, and then NH2. So our Lewis structure might look like the following. Here we have our CH3 group bonded with a carbon that has a double bonded oxygen, or a carbonyl, and this is bonded to an NH2 group. Okay, so this is what our structure might look like. And they want to know what types of intermolecular forces are exerted between these molecules. So first, every molecule contains, well, every covalent bonded molecule will always have London dispersion forces. So these are temporary dipoles that are formed within the molecule. And if we look at the structure of our molecule, you'll see that the carbon is bonded with an electronegative oxygen. So we can draw a dipole moment going towards the oxygen. And we have nitrogen that is also more electronegative than our hydrogens. So we can also draw some dipole moments this way, showing partially negative sides and partially positive sides. So because of these partially negative and partially positive sides, we could have dipole-dipole forces as well. And a more specific dipole-dipole interaction is something called hydrogen bonding. And in order for hydrogen bonding to occur between molecules, we need hydrogen that is bonded to a more electronegative element. So in this case, it is the nitrogen, and this is a specific type of dipole-dipole interaction where these partially positive hydrogens will be attracted to a partially negative force that is found on a separate molecule. So for example, let's say I drew out this molecule again, where we have this partially negative oxygen. And so this partially negative side of a separate molecule will be attracted to a partially positive hydrogen on another molecule. So this is called hydrogen bonding. Okay, so now let's see what the junior tutor said. The intermolecular forces greatly influence the properties of a compound. Different types of intermolecular forces are ionic bonding, which is the strongest and is only applicable for ionic compounds, so we don't have any metals in this compound. So we know that there are no ionic bonding involved. You can also have H bonding or hydrogen bonding, which can be observed in molecules having OH, NH, or HF bonds. Dipole-dipole interactions, which is observed in polar molecules, and van der Waals force, which is the weakest and is only observed in nonpolar molecules. Okay, so they drew out their structure and showed that this molecule has 2 NH bonds, hence it has hydrogen bonding. In addition to that, it also has dipole-dipole interaction because the oxygen atom is highly electronegative than the carbon and nitrogen, so it causes an induction effect. In summary, the expected intermolecular forces between these molecules are hydrogen bonding and dipole-dipole interactions. Yep, so this solution is correct. And I'll also just note that the molecule will also exhibit the London dispersion forces, and like what they mentioned at the top, van der Waals forces. Okay, so question 8 looks like some organic chemistry. And it says, when subjected to ozonolysis, followed by oxidative workup, alpha terpene and I think this is gamma terpenine yields the products below. Hydrogenation of each produces 4-methyl 1,1-methyl ethyl cyclohexane, and provide the structure of both alpha terpenine and gamma terpenine, which both have the molecular formula C10H16. Okay, so this question looks like it would be kind of difficult, but if we think about ozonolysis, this is when you have the oxidation of like double bonds. So everywhere you would have a double bond, this bond would break and form either ketones or aldehydes. So I'm just going to draw out the structure of alpha terpenine and show what I mean by an ozonolysis reaction. So first let's draw the first half of our product. We have this kind of unique structure here. And then we have our 2 double bonded oxygens, like so. So I'm not going to draw out my oxygens here. Instead, I'm actually going to connect it with the second half of that molecule. So where there is a double bond in our second product, I'm going to show it as the same double bond that I already drew. So now I just need to draw a line connecting the two, like so. And this is the structure of alpha terpenine. So now, when this undergoes ozonolysis, so these are the conditions for an ozonolysis reaction. Plus zinc. We can show these products of ozonolysis, and you can see the cleavage of these double bonds, and in its place, they become carbonyl groups. So again, we have what was given in the question, but now the reaction looks more complete. And you can see where these two fragments had originally came from. So now let's try to do the same thing for part B. I'm going to draw out my first fragment. Showing where the double bonds of my oxygen were. And now I'm just going to connect it to the double bonds of my second fragment. So you can see that there's like an extra carbon here, and then it goes down, and then we have this group right here. So it looks similar to alpha terpenine, but it's just a different configuration, and it's known as gamma terpenine. And then I'm just going to draw in my conditions. And again, with ozonolysis, I'm just going to show where these bonds were cleaved to form our two fragments that were already given in the question. But it kind of just shows where they came from. Like so. So now let's see what the junior tutor said. To identify the structure of alpha terpenine and gamma terpenine, determine the degree of saturation by computing the degree of hydrogen deficiency. So this is an additional step that you can do to try to help you answer the question. So they just defined all the terms in this hydrogen deficiency equation. C is the number of carbon atoms, N is the number of nitrogen atoms, H is the number of hydrogen atoms, X is the number of halide. In the case of alpha terpenine and gamma terpenine, which both have a molecular formula of C10H16, they just plugged in all of those values to this equation, and they got 3. So this means that the degree of unsaturation of alpha terpenine and gamma terpenine is 3. And from this name, we know that the compound is an alkene, and from the product of the hydrogenation, the compound is cyclic. Therefore, it can be concluded that the compounds are cyclic dienes. To determine the position of the bonds, or the double bonds, using the products of ozonolysis, followed by an oxidative workup. The general reaction for ozonolysis followed by oxidative workup is as follows. Okay, so they showed just the general reaction scheme and how this double bond now becomes two carbonyl groups. Based on the products of the ozonolysis followed by an oxidative workup of the alpha terpenine and gamma terpenine, the cleavage occurred in the ring, meaning the two double bonds are located in the ring, and they have the structures shown below. Yep, so this solution is correct. Okay, so question number 9. At 25 degrees Celsius, the equilibrium constant for the reaction 2A aqueous makes B aqueous plus C aqueous is 1.64. If the concentration of B is 0.347 moles per liter and the concentration of C is 0.548 moles per liter, what would be the minimal concentration of A in moles per liter required to make the reaction spontaneous? Okay, so let's write down this equation. We have 2A aqueous reacts to make B aqueous plus C. And we also know that the equilibrium constant is 1.64. So we know the concentration of B is equal to 0.347 moles per liter. And we also know the concentration of C is 0.548 moles per liter. And we just need to find the minimal concentration of A to make the reaction spontaneous. So let's write down here, for a reaction to be spontaneous, we want Q less than K. So Q is our reaction coefficient, and it's similar to K, except K is at equilibrium and Q is the actual reaction. So we can write an expression for Q where Q is equal to the concentration of our reactants, or our products, sorry. So concentration of B times concentration of C divided by the concentration of our reactants, which is A. So notice that the balanced equation has a coefficient of 2 in front of A, so that means in our Q expression, A has to be raised to the exponent 2. So now this is our value for Q. And we're also given our K value, which is the equilibrium constant, and it's equal to 1.64. So therefore, Q needs to be less than 1.64. So now let's just plug in all of our concentrations. We have 0.347 times 0.548, and we're looking for the concentration of A. So now let's just try to simplify this using a calculator. You get around 0.19 if you multiply those two at the top. And now let's bring our concentration of A to the other side. And then we'll divide this value by 1.64. And you get around 0.116. And now we just need to take the square root of this value. So switch to scientific mode. Where's the square root function? Oh. So 0.116 square root of that. Right? Let me do this on Google. Okay, so it is 0.34. Okay, so this tells us that our concentration of A needs to be less than 0.341. Let's see what the junior tutor said. For the decomposition of A to be spontaneous, the reaction quote must be less than the equilibrium constant K. So they set up their equation for Q. And already I can see that I think they just forgot to put their A to the power of 2. But they plugged everything in and got the 0.116. I'm just going to say that the explanation is correct. However, since in the balanced equation, there is a coefficient of 2 in front of A, in the final Q expression, the concentration of A needs to be squared. Solving then for the concentration of A gives 0.341 moles per liter. Okay, so those are all the questions for today's session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, you can give it a like and a comment, or you can share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.